What's going on, everyone? My name is Tyler and welcome to my channel. Today we're going to continue where we left off in our series and we're going to get started writing the Pratt Parser. So before we write any code, I want to actually dive into what Pratt Parsing is. A Pratt Parser is a technique for parsing an abstract syntax tree. It is a technique similar to recursive descent, but we'll actually be utilizing a concept of binding powers, which combined with lookup tables provides a really clean way to write a parser. A binding power is simply how tightly a token binds to the things around it. So a plus token will have a lower binding power than a multiplication token. This is similar to precedence, but you can think of a higher precedence as a lower binding power, a lower precedence as a higher binding power. If you compare the table to the Go code on the right here, you can see that it's inverted. The highest precedence items actually have the lowest binding powers. When you combine the binding powers with a handler function, for example, there will be 3 types of handlers in our parser, 2 important ones and 1 for statements. We have a nud and a led. A null denotation, or nud, is a handler which expects nothing to the left of the current token. Examples of this are prefix and unary expressions. Led or left denotation handlers expect something to the left of the token you're trying to parse. So if you encounter a token like plus, you would expect something to the left of it, like 5 plus something else. However, if you run into a token like not, right, the exclamation point token, you would expect that that is a unary token, right? There's not expected to be something to the left of that. Instead, you parse that assuming something's to the right of it. LUD tokens are used for infix, binary, as well as postfix expressions. Later on in the episodes, we'll actually get into those. In this episode, we're just going to write the parser for binary expressions so we can get a grasp of how this all works. Lastly, we have lookup tables, which is where the idea of Pratt parsing really comes together. We define a lookup table for each of the type of handlers as well as the binding power. This allows us to let the parse expression function, which is the heart of the Pratt parsing technique, unravel the recursion for us. So instead of in a recursive descent parser, where we have to manually consider the recursion in each steps, this case, we will handle it with lookup tables, and it'll be a lot cleaner, a lot easier to extend and maintain. So without further ado, let's actually get started writing code for the series. And if you want to follow along with the series and you haven't yet downloaded the code, please feel free to download it in the description down below at tyler-laceby/parser series on GitHub. So without further ado, let's get started. Okay, so the first thing I want to do is I want to create a new .lang file. So I'm going to do 02.lang, and in here we're going to write some code which we'll be able to parse by the end of this episode. So for now, let's parse 45.2 plus 5 times 4, semicolon. And this is all by the end of this episode we'll be able to parse, but it's really important that we get off to a good start. And there's a lot of boilerplate code we actually had to write, which will make our lives incredibly simple throughout every other video. So this is going to be our 0.2.lang file. I'm then going to go into the main.go, change this to be 0.2.lang, right? And I'm going to remove, actually, I'll just make sure it still prints out the tokens. So I'm going to do go run source/main.go. And we see 45.2 plus 5 times 4 semicolon EOF. So our lexer is still working, which if you didn't follow along in the previous 2 videos, that's where we actually went ahead and built the lexer. So what I want to do is create a couple new folders in the source folder. I'm going to create a folder for AST, which is where our tree data structure files are going to go. And I'm going to create a folder called parser, like so. So inside of AST, let's create a file called ast.go. It's going to be package AST. And in here, we're going to define all of our AST types. So we're going to do type statement, and this is going to be an interface. And a statement is just going to be anything that has a method called statement, like so. And so let's also define a type called expression. It's also an interface, and it's going to be anything which has an expression method, like so. So these are going to be our two main types. In the future, we'll also have one for like literal types, etc. So for now, we have that. Let's go ahead and create a expressions.go. Again, this is package AST. And in here, what we want to do is we want to define basically all of the main expressions in our language. So for now, I'm going to do a number expression, which is a struct, and it's going to just have a value field, which is a float 64, like so. And since we want this this number expression to be expression, we need to implement a method for it called expression. So we're just going to do n for like node, and let's just do number expression exper, like so. There we go. And we just need to implement a blank method for numbers. So I'm going to go ahead and copy this for three things. We're going to implement a number, a string, which is just going to have a string, like so, and change this to say string. And this is going to be a symbol, which is going to be a string. And this is also a symbol. Okay, so these are going to be our literals. So and I'm just going to create just a little bit of some formatted comments just so it looks a little clean. There we go. Now what we want to do is define complex expressions. So for example, a complex expression an example of one would be a binary expression. So we're going to do type expression, which is again a structure. And a binary expression contains three things. It contains the left, which is an expression, like so. The operator, which is a lexer.token. And the right, which is an expression, like so. So something that is a binary expression would be 10 plus 5 times 2. 10 would be a left expression, where the expression would be a number. Plus would be the token. And the right-hand side in itself would be a binary expression, where 5 is left, token of star, and right is 2. So expressions can have other expressions, which in turn can have other expressions. So let me implement the function n binary. There we go. So this is all we're going to implement for expressions today. In the future, we'll have a bunch of expressions for all of the different syntaxes in our language. However, looking at the example code, this is a number plus a number times a number. So all we really need to do today is handle numbers in binary. So let's now go ahead and create a new file. And this is going to be statements.go. And again, this is in the package of AST. So just like we defined expressions, we're going to want to define some statements. So what's the statement? Just like an expression, it's anything that implements the statement function. So let's go in here and let's define a few statements. So the first thing we want to do is define a block statement. And this is not a struct, sorry. Actually, it is a struct, my bad. Because it is an implementation. And the body is an array or slice of statement, which means we also need to define a method, n for node, block statements, empty method implementation. There we go. So a block statement is anything like this. So for example, if you have code where you have open block, right in here, there can be 0 to n different statements. So this is a block statement, something with a open block followed by one or many statements. Next, let's also, actually, I think I only want to implement one other one in this episode, and this is going to be an expression statement. And an expression statement is, again, also a struct, which contains an expression, which is an expression, like so. And I'm just going to copy this because I'm kind of lazy. And it's going to be like so. Now, what is an expression statement? Well, if we look at this code right here, we can see all of this is a binary expression, right? So this is a binary expression where the left is a number, the right is a binary expression, where again, the left is a number. You get the idea, right? So all of this was this, left number, right another binary expression. But it was followed by a semicolon, right? So in a language like ours, where we will force semicolons, every single statement has to be finished with a semicolon. That means something like this, foo, is needed to be separated by a semicolon. Foo is what we would call a call expression. So this is a call expression. So this has to have a semicolon. The goal of an expression statement is to take an expression and then terminate it with a semicolon. So this is how we can enforce semicolons super simply in a programming language. So an expression statement is just a statement which wraps an expression. So these are all of the types which we're going to be implementing for today. So let's go ahead and actually get started with that now that we're done implementing the AST types. So what I want us to do is go into the parser, which we haven't, oh yeah, we did create the parser folder. And what I want us to do is actually get started with the parser. So let's create a file called parser, parser.go. And this is going to be package of parser. And what I want to do is first define what a parser is. A parser is a structure. It's not public. I don't want this to be public. I want to instead call a function which returns the AST nodes. I don't want to expose the structure. Inside of this structure, we're going to do tokens, which is a slice of lexer.token. Right? And the position is an int, just like it was inside of the lexer. So we're going to keep track of all the tokens, which we built during tokenization. And inside of here, we have the position. And this is all we need for our parser. In the future, when we handle errors, we might have errors, which is a slice of error, like so. So for now, we're not actually going to be handling errors, but in the future, you might want to keep track of errors and keep parsing. This is how you do it. Let me know in the comments if you do want me to show how you can actually keep track of errors and how you can do hard errors and soft errors. Okay, so now that we have this parser struct defined, let's define a public exposed method called parse. Parse. And this is going to take in we'll actually take in the tokens. Yeah, we'll take in the tokens, which again is a slice of lexer.token. And what we're going to do is return wrong AST. I want to import our AST dot block statement, like so. And for now, let's just do return block statement, like so. So this is going to be our publicly exposed method for parsing. So what I want to do in here is do the body. So we're going to do a body, and this is going to be a type of AST.statements, and it's going to be of size 0. So this is just going to be an array of statements. And that means we can come in here and type body, like so. Cool. Now, the goal of parsing is, in our case, to continue iterating through all of the tokens until we reach the end of the file. So what I want to do is define a few helper methods, which we'll be using for the rest of our time in the parser. So let's go ahead and actually take a look at some of these methods we're going to want to create. So we're going to want some helper methods. So we're going to do func. P is a pointer to a parser. And let's just call this one current token. And this is going to return a lexer.token. And all we're going to do is just do return p.tokens at p.position, like so. So this just returns the current token that we're at. We also want to have a function for advancing. So how do we advance past a specific position? Just like the lexer, how we had advance n, here we're going to have an advance function, which again is going to be a p to a pointer to a parser. It's going to be called advance, and it's going to return a lexer.token. And what we're going to do is we're going to do get the current token. So we're going to do p.current_token. We're going to do p.position++, and then we're just going to do return tk. So this will allow us to advance past the token and return the token at which we just parsed. So let's create a few more methods that we're going to need. One of these is going to be function takes in a pointer to a parser. I don't know why I can't type. And this is just going to be called has tokens, and this returns a boolean. And this check is simply going to do return p.position is less than the length of p.tokens. And what we're going to do with this is check that, one, our position is less than, right, the token length, meaning we're not going out of bounds. And we want to check that p.current token kind is not equal to EOF, like so. And this is our check. Now, what I want to do is actually get a method to specifically do just this, current token.kind. And we're going to want to call it p.current token kind. So let's go ahead and create that method. And we're going to create it right here. Func. In fact, let's actually just straight up copy this. And all we're going to do is we're going to change this to say kind. This is going to be a lexer.token kind. And we're just going to do return p.tokens.kind, like so. Or we could just do p.current_token.kind, like so. There we go. Perfect. So that's our has tokens method. And for now, that's all we need. So let's continue back to the parser parts right here. And this is going to be pretty simple. All we want to do is while we still have tokens, we want to continue parsing the statement. So what we're going to do is we're going to do for, and while p.parse. Oh, sorry, we need to create a parser instance. My bad. Create parser, like so. And we're going to pass in the tokens. Okay, my bad about that. So yes, we do need a create parser method so that way we can actually, well, have access to a parser. So let me just really quickly create that. It's going to be called create parser. It's going to take in tokens, and this is just a token, a slice to a lexer.token, and it's going to return a pointer to a parser. Since we're going to be dealing with pointers a lot with this parser stuff, I like to just return the pointer like so. And all I'm going to do is do return reference to a parser like so, where we're just going to say tokens is like that. And that's really all we need to do, since position will automatically get set to 0. Perfect. So that is how we create our parser. Now what we want to do is we want to go ahead and we want to iterate as long as we have tokens. So right here, we're just going to do while p.has tokens. So while too few values in struct literal, does it not like... Okay, it does not like whatever I did there. There we go. Anyway, so while we have tokens, what we're going to want to do is we're just going to do body equals appends, and we're going to append a function called to parse statement, passing in our pointer. Now we haven't created this parse statement function, so let's go ahead and create a file called statement.go. And basically we're going to have a file for statements, expressions. In the future, we'll have a statement for types, but for now we're not there. So we're going to have a function called parse statement. So I'm just going to go ahead and create this func parse statement. It takes in a p, which is a pointer to a parser, and it returns an AST dot statement, like so. And for now, I'm just going to panic saying not implemented. Perfect. So there we go. Okay. So now that we have this, basically what we want to do is append the body to this. And the body is a capital B, and so is this. There we go. Okay, so let's quickly go over what we're doing here. And yeah, it does not like this, so I'll just keep doing like so. Okay, so what we're doing is we're creating a parser instance. We're then just going to call parse, which is just going to instantiate a body, create the parser, and iterate while we are not at the end of the file. Then we're just going to return this block statement, which is the whole body of our program. We've defined a few helpful methods like getting the current token kind, has tokens, and advance, which we'll be using throughout our time with the parser. Now, what we want to do is actually now get to setting up the lookups and binding powers that I was talking about in the beginning of the episode. So this is the fun part. So we're going to set up lookups.go, and we're just going to say package parser like so. Okay. Now, what we want to do is define what a binding power is. So we're going to say type binding power, which is an int. And if you recall from our intro to the video, we defined a few different types of binding powers. So I'm just going to come over here, copy that. And here you can see the different binding powers which we will be using. We had a default binding power, which is 0, and it goes up to primary, which is 10. Now, these binding powers are how tightly a certain token or tokens in a certain group bind. So for example, things like primary, which would be like a number or whatever, bind very heavily. Multiplicative binds tighter than relational and additive, etc. So what we want to do is define these binding powers, and this is how we're going to do it. So we're going to have a binding power enum, basically. Perfect. Now what I want to do is go ahead and define 3 different types of types. Now, let me also not copy it from here. This should be AST. There we go. Like so. Okay. So we've defined the binding power. It's just an enum, like so. Then what we want to do is we define what a statement handler is, a nud handler, and a let handler. These are basically just functions. So we're going to create a function to parse every single type of token that we can think of. And these are going to be the ways we do that. So I'm also going to go ahead and define 4 different types of lookup tables. Again, lexer is like so. So we have a statement handler, which takes in a parser instance and returns a statement. We have a nud handler, which takes in a parser instance and returns an expression. A led or left denoted handler is going to take in a parser, the left denoted expression that we've already parsed, and a binding power, and it's also going to return an expression. Then we just have a map for each of these types, taking in a token kinds and returning that value. So the key is going to be the token kinds, and the value is the handler itself. Same for binding power, it's just going to return the integer value of that binding power. And with this, we can actually then, in the global scope, create 4 new lookup tables like so. So we have a BP lookup, which is this one, nud, which is this one, led, and statement. Now, what we want to do is also create a few helper methods, so that way we can actually go ahead and create different types of, so that way we can instantiate, for example, a binding power lookup, led lookup, nud, etc. So what we want to do is define something in here for a led function. So here we're creating a function called led, which just instantiates the binding power lookup of that token kinds to be the binding power, and the led lookup kinds to be a led function. So it takes in a function as an argument. We then have 2 more similar functions for nud and statement. So we have a led, a nud, and a statement, like so. So now that we have all these, we can actually create a function called create token lookups. And this function won't actually return anything, but what it'll allow us to do is start setting up these parsers now. So let's call this function from inside of our parser. So when we call create parser right here, what I want to do is first call create token lookups, like so. Let's go back to create token lookups and start figuring out how we're actually going to start doing this, right? So what I want to do is first handle the case of a number. So when we reach a number, how do we want to parse this? Well, for this, we're going to want to create something over here. There we go. So when we go into the create token lookups, let's create something for literals and symbols, like so. And a number is a literal. So what we want to do is say a nud of number. So a nud for the number, it has a binding power of primary because a nud is a primary expression. And the function is something like this. So the function is going to return an expression. In our case, we basically want to get the current token, right? So what we want to do is we want to call a function like, we basically want to get the current token kind, right? So we want to get the current token kinds. So let's just switch p dots current token kinds. And what we want to do is if the current token kind is a number, which we already know it is here, but I'm trying to generalize this so we can use this exact same function for all of the literals and symbols, then if it's a token kind of number, for example, then we want to try to parse the number using strconv dot parse floats. And this takes in the string, so we're going to do p.advanced dot value and the bit size, which is 64, like so. And this should return a float, or it could error. In our case, we're not going to check the error, but it could. And once we have this number, then what we can just simply do is type return ast.number expression, where the value is the number, like so. And this right here is how we can parse numbers. So one thing we could do, for example, right, is we could just do this. We could create a lexer handler for the number. We copy this, copy it 3 times, and here we would do it for string. And for symbol, lexer.identifier, there we go, right? And then for string, we could just do this. So we could actually just remove this line, because for strings, we don't have to do any parsing, right? Whoops, there we go. And we can just say string expression, the value, right, is going to be p.advance.value. And we can just copy this as well and change this to ident symbol expression. Now, if you notice, the issue here is that it's basically the same code we've duplicated 3 times. Ideally, we want to create some way to do this more generally for all primary expressions. So let's go into the expression.go and handle this the way we would like to do it. So we're going to have parse primary expression. It's going to take in a p, a pointer to a parser, and it's going to return an axt.expression. I need to import AST. And what we're going to do is we're going to do that switch case I was trying to do earlier. And we're going to switch on the current token kinds. If the case is a number token, right? If it is a number, then we're going to do what we were doing before. So we're going to get out the number, like so. Right? And that is our case. If the case is not a number and it is a string, then we need to handle it the way we handled the string, right? I'm just going to paste this. And I'm also going to, go ahead and try the case for if it is an identifier. And we had symbol, and like so. So these are the three cases. We then want to have a default case, where we just panic. And what we're going to do is we're going to do an fmt.sprintf. And we're just going to say cannot create primary expression from brax s \n. And what I want to do is do lexer dot token kind string of p dot current token kinds, like so. So we're basically just going to say, hey, if we're calling this and it's not a number, a string, or an identifier, let's just throw an error saying, hey, this doesn't make sense, right? And now what we can do is just use this singular function here in place of all of these three. So currently where we were doing this, right, it took in a nud handler. What is a nud handler? Well, a nud handler is a function that takes in a parser, pointer, and returns an expression. That is this, right? Takes in a pointer to a parser and returns an expression. So now what we can do is we can just come in here and just put that there for all three of these. And we can delete that line like so. And just like that, we now can handle numbers, strings, and identifiers in our language. So whenever our parser encounters a number, string, or identifier, they can all share the same function just by using this. We switch on the current token kind. The current token kind is either a number, a string, or identifier for us to get to this point. And then we just parse it as we expect, return the AST value, and voila. Now, one thing you're probably wondering is how do we parse binary expressions, right? So how would we parse the plus and the multiplication and all that? Well, glad you asked. So what we want to do is go into the lookups and define a few things for binary expressions, right? So what I want to do is define our logical, relational, additive, and multiplicative binary expression handlers. So first we're going to do logical. And what we're going to do is we're going to do led. So we did nud because a number or all these things, they don't have to have something to the left, as you can see right here. They don't expect it. However, pluses and stars and all that, they expect something to the left. So we do our led, left denoted stuff. So first we take in the token kind. For a logical, let's do ands first. Let's say it's of type logical. And the function handler for this is going to be parse binary expression. We haven't defined this, but we will in a second. So let's define the other three logical operators, which is or and dots. This isn't necessarily a logical operator, but dot syntax is the lowest precedence operator. So if we see something like this, 10 ... math, right? That means we want to iterate from 10 to this whole quantity. So this requires this to have a super low precedence to be able to parse all that. So that is the logicals. Next we have relational, T-I-O-N-A-L, can't spell. And these have a similar thing. So we're going to do lexer dot less. It's going to be a relational this time. And again, parse binary expression. I'm going to copy this a few more times. We're going to have less equals, greater equals. We need equals as well, and not equals. I knew I missed one. Like so. And these are all relational operators. Again, we haven't defined parse binary expression, but we will once we define the rest of these. Lastly, we want to do additive and multiplicative. So if you notice something here, logical has a binding power of 3. Relational has a binding power of 4. Additive has a binding power of 5, and multiplicative has a binding power of 6. So this is why we're defining them like this, because if you recall from our table at the beginning of the video, these are the opposite of the order of precedence. So for example, a logical operator has the highest precedence, while something like a multiplicative has the lowest precedence. So let's now go ahead and define our additive and multiplicative. So we're going to do lead. We're going to do lexer dot, let's do plus first for add. It is a additive. Beautiful. And what we want to do is do parse binary expression. We're going to copy this, and this is going to be minus. We called it dash, right? Then I'm going to copy these two, and we need to define one more. So for additive and multiplicative, these are the two additive. Next, we need to do multiplicative for star slash and percent for modulus, right? So most languages, these are multiplicative. In most languages, a percent has the same precedence as star and slash. They're both on multiplicative operators. So there we go. This is how we define additive and multiplicative expressions. And you notice all of these all use the exact same method, parse binary expression, which again, we haven't defined yet, but we will right now. So let's go into expressions.go. Here's parse primary. So right above it, I'm just gonna, we'll go right below it actually. But right below it, what we're gonna do is we're gonna define parse binary expression. Now, if we recall what this has to be, this is a nud. We are dealing with lead, sorry, right? So it takes in a pointer to a parser. It takes in a left, which is an AST, AST.expression, and it takes in a BP, which is a binding power, and returns an AST.exp, like so. Okay. Now, what is this? How do we handle this? Well, if we think about how a binary expression works, by this point, that means we've already hit the left thing. So first thing we need to do is get the token or the operator. And I'm just going to do operator token is p.advance. Why advance? If we recall, advance eats the current token and returns it. So this is now a token. Beautiful. Now what we want to do is we want to parse the right-hand side. We haven't defined this method, but this is the next one we're going to define. And it takes in the p and the binding power. And then once we're done, we just do return binary expression, where the left is, well, the left, the operator is the operator token, and the right is the right, like so. Now, the only thing we have to do is define this method right here, and then we're completely done with our parser. So let us go ahead and actually define arguably the most important method in the entirety of the Pratt parsing. So let's go, we already are in expressions, so I'm just going to minimize this file. And at the very top, we're going to define this method. And it's going to be a function. It's going to be called parse expression. And it takes in, again, a pointer to the parser. The reason we take in a pointer is so we can mutate it. And it takes in a binding power, which is, again, a binding power. And it returns an AST.expression. So this will always parse an expression at wherever we're at. Now, what we want to do with Pratt parsing is first we parse the nud. It assumes that if there's nothing to the left, then you parse a nud. Then, while we have a lead and the lead and the current BP and the current binding power is less than the BP of current token, we want to continue parsing left-hand side. This is the whole principle behind Pratt parsing, and I'm going to walk you through it now. So first thing I want to do is I want to get the current token kinds. And what we're going to do is we're going to do p dot current token kinds, like so. Next things first, I want to get the nud function, and I want to check if it exists. And the way we're going to do this is we're going to do a nud lookup of the token kinds, like so. And if it exists, this is a Boolean, and this will return the handler for the current token we're at. So what is this doing? Well, if we look at our example of 10 plus 6 times 2, the current token, right, the first time we call parse expression, is a number. So it's going to check, does the nud lookup contain a function for a number? Well, if we look in our lookups, we see we've defined a nud for numbers, strings, and identifiers. Good. So that means this will exist. So first thing we want to do is we want to check if it does not exist. If it does not exist, there's a problem. We should have this exist. So we're going to do panic. And what we're going to do is we're going to do an fmt.sprintf. And we're just going to say nud handler expected for token %s s\n. And what is the token? Well, we're going to do a lexer.token kind of p, currents token kinds, like so. So if it does not exist, we want to get out of here. This should never happen as long as you have valid syntax. Now, you could produce a better error message, but that is up to you. If you held on to the locations of the position inside of the token struct, for example, you can hold on to the line number, the start and end positions, you can produce a lot better errors than this right here. So if it does not exist, we do that. If it does exist, right, then what we want to do is parse whatever the nud handler is for this token. So for number, it's just going to return that number. So what we're going to do is we're just going to call nud function, and we're just going to pass in the parser, which is p. And this right here is going to return the AST for a number in this case. And by doing so, it's going to advance the position from here to here. Now that it's advanced that position, what we want to do is iterate over the current tokens in the binding power lookup of p.currentTokenKinds. Notice, this is not going to be the same thing as this. Once we call the nud function handler, we're going to advance. So we will be at a different current token kinds. So we started at 10. This now contains a numeric literal of 10. The current token kinds will be plus. So we're going to iterate. So we're going to get the current token kinds binding power. So the binding power of plus is additive. We're going to get that binding power, and we're going to just make sure it is greater than the current binding power. Now, the reason we do this is we need to always try to traverse right. If we do not always try to traverse right here, we will have issues with expressions like this, where this side of the tree is lighter than this side. So this is what we do. We say, hey, keep traversing and keep parsing left as long as the current binding power of what we were already parsing when we got here, so by default, this will be default. Keep traversing right. Now, what is that going to do? Well, what we're going to do is we're then going to say token kind is equal to p.currentTokenKinds. We're then going to get the led function, which is, again, we're going to have an exists like so, and we're going to do led lookup at token kinds like so. We are going to basically copy this statement right here. And if this does not exist now, right? So if this does not exist, it is not a nud, it's a led now, right? And we just do that. Lastly, what we want to do is we want to replace this left with the new left. So this is how we unroll our recursion all the way through. And we're just going to say left is equal to led function, where we pass in p, and it takes in the previous left. This is why this works. It takes in the previous left. So we're going to pass in left, and the binding power is BP, because we want to make sure we keep using this binding power all throughout. Then once we're done, Do not mean to do that. Once we're done, we can just return left. Now, let's quickly go over how this actually works in the real world. So when we first call this, assuming we pass in a binding power of 0, which is what we'll do in a second, it's going to hit the first token kind is going to be number. The token kinds is going to be checked. It's going to exist. So we're going to have the number handler. If we recall the number handler's parse primary expression, it's just going to return an ast.number expression. So that will be left here. ast.number expression will be in the left. The position, because when we do that, right, we advance. So the position is going to go to this token now. So it's going to be at plus. What it's going to do is it's going to look up the binding power of the plus token. If we look in the lookups, the binding power of the plus token is additive. 5. Okay. Is 5 greater than 0? AKA, is it greater than the default binding power? Yes, it is. Because 0 is obviously less than 5. So we get the current token kinds. We already know we're at a left or a plus here. So now we do this. We get the lead function. Does the lead exist for a plus? Well, as we saw here, it does. We've defined the lead, which uses parse binary expression. So we go back in here and we know this is good. So we get the left-hand side. Now, we then call lead function passing in our previous left. If we recall, at this iteration, this value is the left of the plus token. It is a number expression. We then call, because our current token is a plus, we then call binary, right? So this is a number. This is 0. We're going to get the current token, advance past it. So this is the plus token. The right-hand side, what we're then going to do is repeat this process. So now the right-hand side, now all of this has been parsed. It's going to get a 6. Nud. Boom. It works. Beautiful. What's going to happen is we're going to check if it exists. It does. This is going to be a number expression. We're then going to try the right-hand side. It's going to be a star. It's going to parse in until eventually there is no binding power for anything less than us, so we're just going to return the left. The 6 times 2 will be a binary expression, which will get passed back through here as the right-hand side. Then this will be able to return out a binary expression where the left is the number, the right is the plus, and the right-hand side is another binary expression. And this right here is how we unravel the recursion. Instead of doing recursive descents manually, we use this technique of Pratt parsing to do it. So now that we're almost done, we are almost done. We are so incredibly close. Now what we need to do is actually call parse expression, as we don't ever really do this. Instead, what we do is right here, we call parse statement. Well, parse statement we haven't implemented. So let's go ahead and finally implement parse statement. So what we're going to do is we're going to do an stmt function. We're going to check if it exists. And just like we did with here, we're going to do a lookup. And what we're going to do is we're going to do the stmt lookup. And we're going to check the p.current token kinds. If it exists, then what we want to do is we just want to do return statement function passing in p, like so. So if we had a syntax like this, let x equal 10, let is a reserved keyword, so we would define a statement handler for it, we would get here. However, if we just have this 10 plus 5, right, this 10 is not a statement, it's a number. So we will go past this, and what we're going to do is we're going to do expression p.parse expression. We're going to do p, and the binding power will be defaults. Then we're going to do p.expect, which we haven't created, but we will in a second. So we're going to do p.expect. And what are we going to expect? Well, we're going to expect a lexer dot semicolon, like so. And then we're just going to do return expression statement, where the expression is the expression here. Beautiful. Now let's just go ahead and create p.expect. So we're going to go to the parser.go, and we're going to create a few little helper functions to allow us to expect a token and produce a nice little error. So what we're going to do is first we're going to create a function, which is a parser, and it's going to be called expect error, like so. And it's going to take an expected kind, which is a token kind, and it's going to contain an error, which is going to be anything. And expect is kind of like advance. It's going to try to advance, and if it can't, it'll throw an error. But it will still return the token kind we're at. So what I want to do is I want to do token p dot current token. Then we're going to do kinds p dot not token dot kinds, like so. If the kind is not equal to the expected kind, right, then we know we have a problem here, right? So if it makes it to here, that's bad. If it doesn't, then we should probably just do return p dot advance, right? So we're just going to advance and return the value. Okay. If this is an issue, then what we need to do is we need to create an error. But first, we need to check if there's already an error that's been passed. So let's do if error is equal to nil, meaning we didn't pass a default error. We want to produce our own kind of error. So we're going to do error colon equal to fmt dot sprint f, and we're going to do expected %s, but received %s instead, and then backslash n, like so. Now, expected, well, what did we expect? Well, we expected token kind string of the expected kinds, right? So I'm going to just zoom out a little bit so we can see this better. So we expected a string. What is the string? The token kind string of what we were actually expecting. And what did we receive? Well, we received a lexer.token kind string of, well, kinds, like so. So this is just a nice, helpful little method to generate an error string if we didn't pass one into this function, like so. So if we passed in anything else. Then what we're going to do is we're going to go ahead and call panic error, like so. And, oh, I need to assign, like so. There we go. Perfect. And this is our expect error function. Now down here, we can define a function, p parser, and then we call it expect. And this is going to be expected kind is a token kind. And the error is going to be nothing because this is just going to be our general helper. And we're just going to do lexer.token. And all we're going to do is we're just going to do return p.expect error. We're going to pass in expected kinds nil, like so. So if we want to give a custom error at some point, we can call expect error. If we just want to generally say, hey, I expect a token, we can just say this. And that's what we're going to do. So if we go back to the statement, we say, hey, we're expecting a semicolon. If anything other than a semicolon is the current token, while we try to advance past it, it'll throw an error. And that's basically all we need to do to handle this. So this is now going to be our parser. So let's now go ahead and actually give this a try and go to the parser go. And let's take a quick look and just make sure we call parse inside of the main.go file, right? So here we have the tokens. And what I'm going to do is I'm just going to do ast colon equal parser dot parse, and we're just going to pass some tokens like so. And this will give us the AST very nicely. Now, what I want to do also is I want to print out this AST. And it's kind of hard to do that by default using Go standard library. So what we're going to do is we're going to do go gets, and we're going to do github.com/sanity.io/litter. Hit enter, and it's going to add this package to our go.mod right here. And that's beautiful. So now that we do that, let's go into the Go main. And what we're going to do, right, inside of the main is we're going to use this package called litter. So we're going to do litter dots, and we're going to call dump. And we're just going to pass in the AST. And this is going to very nicely print out our AST. So let's give this a shot. So let's just do go run source main.go. And look at that. That is a beautiful AST right there. So let's kind of look through this and just see what it looks like, right? So we have a block statement as we expect. We then have the body where the first element is an expression statement. Why is it an expression statement? Well, if we look through here, it's because it's a semicolon. In fact, if I remove the semicolon, we get this: panic, expected semicolon, but received end of file instead. And you can imagine how we can improve these errors to show the line number, show a snippet of code, etc. instead of panicking. But if we run this again, we get that. So the left is the value of 45.2. Yep, that looks correct. The operator is plus, lovely. The right-hand side has a binary expression of the left of 5, nice, star, and right of 4. So we can see that the precedence is indeed prioritizing the right-hand side because this has a higher binding power than the plus. So I hope you found this video useful. This is a lot to take in, so feel free to review the video, watch it again. I will leave a link in the description down below to this code right here, as well as a link to my Discord server, where if you have any questions, feel free to directly reach out to me. I am very frequent on there, always answering questions, and I love to talk to you guys. So I will talk to you in the next episode, where we will actually talk about variable declarations, and we'll learn how to parse some more complicated ASTs, and it'll be a lot simpler. Now that we have the lookups defined, basically all we have to ever do to parse the syntax is define a nud, a let, or a statement function, and then just create that function like this. So just as it was this easy, parse binary expression works because we created it, and now all of these can get parsed by one function. So I hope to talk to you in the next video. In the meantime, happy coding. Bye.